Yeah, so lately I've been getting more and more interested into algebraic questions, and now very recently also in questions of complexity. So this was very interesting so far, the conference for me. If you have any questions, as usual, please immediately interrupt. So sadly, Dennis is not here, but then somebody else has to take his place and ask questions. Please do. I think it's very good if we have such interaction. So I want to speak about dynamic programming and Hopf algebras in the context of iterated sums. Iterated integrals probably is known to many of you here in analysis of ODEs or analysis of SDEs and rough path analysis. Lots of people here are working with that. I'm interested in the aspects related to machine learning. So in the last 10 years, they have been applied quite successfully in time series analysis, machine learning. And I just give you a bunch of references. Just note that in the end here, so now it's starting to also appear at NeurIPS. So it's gaining traction. So I should tell you what an iterated sum is. It's just what's written there. Z is the time series, yeah, real valued for the moment maybe, semi-ring valued in a second. And then you form the sum. It's just a sum you calculate. And of course, if you this looks like a discretization of an iterated integral. There's a very close connection. But in some sense, iterated sums are a bit more powerful. So I would like to use them here in this talk. So yeah, but the question first is, why are they so successful? So if you ask Terry Lyons, it is because they're universal approximators, integrals now. It's this universal ODE that you spoke also about, yeah? So you give me a path, a continuous curve now, smooth, and I can solve one ODE, and with this ODE solved, I can solve all the ODEs driven by this path. This is the signature. And so you have this universal approximation property. And this is one reason why it's so successful. This line of reasoning does not work for iterated sums. And so this made us discover two other very relevant, in our opinion, reasons why they work, why they're so successful. I give you two reasons, yeah. So the first reason is that they do extract meaningful information. And this is chronological information. So we're talking about time series. So chronological information is something like the following. I give you an itinerary of a person flying from city to city, and I asked, was this person in Rome? And then sometime after in London. That's a chronological question, yeah? Something happened, and then something else happened sometime after. And these iterated sums are very good at capturing this kind of information. And I want to demonstrate this. It's very simple. But before doing this, I want to answer a simpler question. And this is, did a person go from Rome directly to London? Yeah, just the next day, fly to London. And this is an easier question. And it gives us an opportunity to look at how classical machine learning machine learners maybe would answer this question in a neural network with, for example, a convolutional neural network. Yeah, convolutional neural network were the state of the art up to maybe 5 years ago for everything relating to image recognition. And they're still at the top of the stack, so to speak. But other methods, I mentioned one of them later, have become quite competitive. Anyway, a convolutional neural network is very easy to explain in the picture here. So I have my data. This is my travel itinerary. Hamburg, Berlin, Rome, blah, blah, blah. And then I scan over it with a kernel of size 2 here. The kernel is now Rome, London. I move over it with my little kernel, and I see whether I get a hit. So this is a 0. I get a 0 down here, and here I get a 1. This is, yeah. And then afterwards I don't care anymore, because now I just have to take the maximum of the numbers here in the last row. And I know, yes, this person was in Rome, and then the next day she was in London. Yeah. So now let's modify this. How would you deal with this chronological question that I ask? I want to, for example, get a positive here. This person was in Rome, but then Berlin, Amsterdam, and then in London. This I cannot detect with this procedure I just told you. Well, I could detect if I make the kernel very large, yeah, but it has to be as large as the distance between these two cities. So one layer CNNs, they have difficulties of detecting this. It's a chronological question, and you can answer it well. You just ask all the questions like before, but it's just more questions you ask now. You asked, were you in Rome at the first day of your visit, and in London the second day? No, the answer is no. Were you in Rome the first day and in London the third day? Answer is also no. And I go on, and here I get a hit. Yeah. So now the kernel doesn't go over consecutive time windows. It goes over all n choose 2 possible ordered tuples. And you might already see a problem that might appear here. It's a combinatorial problem, so explosion. Yeah? N choose 2 is a lot worse than n. If I have 3 cities, n choose 3, and so on. But we'll get to this in a second. Actually, we'll get, I think, to it right now. Before I quickly just tell you what this has to do with iterated sums. This was an iterated sum, my procedure here. I just have to do it over the proper semi-ring. So instead of plus, I use or, and instead of times, I use and this is a semi-ring, the Boolean semi-ring, yeah? And then this expression I've written here, it goes over all ordered tuples I1, I2, and ask at the first time point, were you in Rome? And at the second time point, were you in London? And then it takes the or over all of these. This is an iterated sum like I had on the first slide, just different symbols. So this is a chronological question that can be answered with iterated sums. Okay, but now on to the second question. This is complexity is bad, so this is n squared, but we can do better, yeah. And it's a one-line proof here. The good thing in the semi-ring or in the field or wherever, you have associativity and you have distributivity. And when we use this here, we can bundle. So first we have a little bundle here where we ask, have you been in Rome up to this point? Then this question's answered. And this question costs me n. This is linear, yeah. I just have to go through the list of all cities. And after this question is answered, I have, and afterwards, have you been in London? Again, I have to do this n times, so it's n plus n, this linear cost, yeah. So we have reduced the problem of cost n squared to a linear problem. And for 10 cities, we would have reduced the problem of complexity n to the 10 to, again, a linear problem. So this is a very baby version of dynamic programming that works here, yeah. And it's because of associativity and distributivity. So these are the two reasons. You have a question, yeah?
If you asked about 3 cities, then would it be exponential? Because it looks a lot like 2 sets.
Yeah, okay. This is one slide I deleted. So it is always linear with the. So what did you say is 10? If you have 10 cities, then it would be 10 times n. Because you always do this iteratively, right? I could now iterate this procedure here, go out. What is not possible is to do arbitrary stuff. I deleted this, but if we look at the first line here, I cannot just replace this expression. Do you see this? Yeah. I cannot just what I want to say. Let me come back to this when I have the theorem on board, the corollary. Yeah. So this formulation is linear cost. It doesn't cover completely a 2 set or something. Yeah. It does not. Because, well, I don't know enough about 2 set, but I guess we don't have the negation in there.
Can I make a comment? I think the polynomial that you wrote at the beginning looks like an elementary symmetric polynomial, right?
Yes.
It's evaluation of elementary symmetric polynomial.
Yeah. This is just, yeah, exactly. Yeah. And exactly, symmetric polynomials are a special case of this.
Very naive, if you look at it very naive, it looks like a difficult polynomial, but it is not, for many reasons, and you showed one reason.
So I would ask, where does this concept of difficult polynomial appear? Is this something that exists?
Yeah,
Yeah,
maybe
okay.
let's talk about it.
Okay, this is very interesting, yeah. So that's exactly what's happening. It looks difficult, you look at it closer, it's very easy. And not only is it easy, it tells me something about my time series, chronological information. Yeah. And I essentially gave you a proof here. This is one corollary in the paper with Kurush, who's also here, and Nicolas Tapia, that this works over any semi-ring. I can form this iterated sum here. And now I moved already away from the algebraic setting, so I can put little f's there. Yeah, I could put powers there, z to the power 5 and so on, or could put nonlinear functions, sinus of zi1 times cosinus and so on. This doesn't change that I can do this dynamic programming principle. What is not possible, and this is coming back to your question now, is I cannot put all these z's in the same f. Yeah, I cannot sum over all I1 smaller than I2, f of xi1 comma xi2, because then you can construct honestly hard problems with that. Yeah, you need this algebraic factorization here. Yeah, you need the distributivity. You need to use the distributivity. And just a small advertisement for iterated sums versus iterated integrals. For iterated sums, it's very easy to switch the semi-ring. Yeah, and essentially for iterated integrals, you can do R, and you can do C, both fields. Yeah. Probably you can do a bit more, but you definitely cannot do the Boolean semi-ring, iterated integrals, or you cannot do the tropical semi-ring, min plus or max plus. So this you get for free somehow in the iterated sums world. What you also get for free is that you can do this here. You can put little thetas there, f of theta 1, f of theta k. Dynamic programming still holds. But now I can learn these. Yeah, these f are now my parameterized functions, so I can put them in the learning pipeline. I can learn these, and it's immediately learnable. With iterated integrals, you can do this for linear functions there, but if you do nonlinears there, you have to do the chain rule, and it gets more complicated. Here, it's very cheap. Yeah. I promised some algebra, Hopf algebra, and how it relates to this dynamic programming. So let me sketch this. Now I go back to the algebraic setting. So we talk about polynomials, not these f's around and so on, because I want to have an algebra here. So I collect all of these values. So maybe let's look at an example. It explains nicer what's going on. So you give me a word, 537. And then I calculate the corresponding iterated integral over 3 time points, I1, I2, I3. At the first time point to the power 5, second, and at the last time point to the power 7. This gives me some number. Maybe it tells me something about the order of the visits to these cities or something else. And I do this for all these tuples. And I put them all in a big collection. And this we call the iterated sum signature. By the way, if you switch here the semi-ring, this was here, I mean, I wrote it like it's real numbers. If you switch, for example, to min plus, then you get this expression here. For people who have done some machine learning, so this looks now like a max pool or min pool operation, which is also a fundamental building block for convolutional neural networks. And in the Boolean semi-ring, which we studied with the city example, it would look something like that. Okay, so I have a linear, so I take now the linear span of all these words. 537 is one direction, and then 779 is another one. The empty word is also one direction. I take the free module over S, and I define this linear function here, iterated sum signature, which spits out these iterated sums. Here it's again maybe in a more formal way. I think of these, we usually think of these as formal power series in these words, where in front of the word I put the coefficient that calculates the iterated sum. So I would put here in the sum the word 537, and in front of it I put a real number, for example in the real ring, which is this sum I calculated on the previous page. And I do this up to infinity, all these numbers. So far this is just writing down this differently, but it's nicely compatible with algebraic structures I can endow these words with. So Claudia is a specialist in this area, so you have a nice algebraic structure on these words. This is a Hopf algebra. It's the quasi-shuffle algebra, and you have a product there. And with this product, it turns out you give me two of these iterated sums, very complicated, two very different. These are now real numbers. Let's stick to this case. I multiply them, and I find this number again in my signature. So this nonlinear expression, so this product, is again a linear expression. So everything is linear because because we have an integration by sorry, how's it called? Summation by parts formula. Yeah, for iterated integrals, it's a shuffle identity. Yeah, which follows from an integration by part formula, and for iterated sums, it's a summation by parts, which gives you the shuffle identity. So it's highly redundant is another way of saying this. This ISS, you find the same information again and again and again. In Hopf algebraic terms, this is a character, or algebraic terms, this is a character on the algebra of, on the quasi-shuffle algebra. Okay, let's leave that for a moment. This is nice to know. What is more relevant for us for the moment is chance identity here, which tells me the following. So if I want to calculate the iterated sum from time s up to time u, I can take a pit stop in the middle at t. Yeah, so I first calculate everything I need to know from s to t, then everything I need to know from u to t to u, and then I can combine this to get the whole interval. Yeah, so let me explain what's going on here. So you have these words of integers, and of course I can concatenate words. And this is what's written here. So I sum over all possible deconcatenations of the word that I'm interested in. So I have an example here. Here it is. Yeah. So you concatenate 3, 2, and 4 gives you 3, 2, 4. So if W is 3, 2, 4, then one occurrence here would be 3, 2 on the left, W prime, and the 4 on the right, W prime prime. So the details here are not very important, but what is important is that this is, you can already see here that the dynamic programming principle is emerging, yeah? This is actually a lot more than a dynamic programming principle. We'll come to this in a second, but let me say again, if I want to know something about a large interval, it's enough to know over the two small intervals. That's enough. So sub-problems give me the whole problem if you want. Here's the for those who are interested, the quasi-shuffle is like shuffling words, but the quasi comes from the fact that you're allowed to merge letters, yeah, so they can swallow each other. So, for example, 3, 2 shuffled with 4, the shuffle is easy because you put the 4 at the end, in the middle, or in the beginning. This gives you the 3 letter words here, 3, 2, 4, 3, 4, 2, 4, 3, 2. These are the shuffles. And then I have the swallowing, so or the mergings. So the 4 can merge with the 2, which gives me a 6. It's additive. And it can merge with the 3, which gives me the 7. And these extra terms here come from the fact that summation by parts, you have an extra term, yeah? Integration by parts, you have f times g is f dg plus g df. That's integration by parts. But summation by parts, you get a diagonal term, which is not, not appearing for integration. Anyway, it's not too important. The algebra keeps track of this for us. Yeah. And as I already mentioned, the chance formula gives us a DP algorithm. It's super simple, but let me give it to you anyway. So I I want to know the ISS from 0 to t, so the iterated sum over the whole interval for word ABC. Then I apply the formula from the previous slide. I decompose ABC in all possible deconcatenations. So ABC to the left, empty word to the right. I haven't written the empty word here. Then AB, comma C, A, comma BC, and empty word, comma ABC. And now the question is, where do I split up? Well, I split up exactly one day before, or one time step before. So t minus 1, I split up. And then I get here the recombination of the two intervals. And one of these intervals now very small, because it goes from t minus 1 to t. It's just one time step. And this has the effect that a lot of these terms disappear. Let me explain one of them. For example, the last one here, yeah, the very last one here. So this asks, please calculate this iterated sum ABC in the interval from t minus 1 to t. Well, I have to squeeze 3 time points in there, right? I had the sum over I1, smaller I2, smaller I3, and then I did something at these time points. But I cannot squeeze 3 time points in there, so this vanishes, yeah. So what's left is the big guy up to now, where I calculate what I had, and then I have this additional term which tells me how to move to the next step. I can also, the last line you can also explain immediately. You don't need the algebra for this, yeah. So if you want to put 3 points, I1, I2, I3, somewhere in the interval from 0 to t, either all of them are in the interval 0 from 0 to t minus 1, or the very last one is t. That's all that can happen, yeah. That's the dynamic programming principle. We get here in a complicated fashion from Chen's identity. So in some sense, Chen's identity encodes in a Hopf algebra and in a bialgebra so far a dynamic programming principle. I always said Hopf algebra, should have said bialgebra, because I said we work over a semi-ring, and over a semi-ring you don't have additive inverses. So then an antipode does not necessarily exist. But if you're in the setting where we have additive inverses, we have an antipode, yeah, and then I can take inverses. And without going into details, you can get from this that so morally you get from this that these characters, these ISS, they're all characters, so they're group-like, and they have an inverse. The antipode allows me to invert this. And if I spell this out, I skip over a tiny bit of detail here. This tells me something much more interesting than the dynamic programming principle we had before. So we have to look at the parameters here now. So we really have to, that's why they're colored. So I want to calculate the ISS from S to U. And now I pick this middle, I can pick, it was U in the previous one, but T, I can pick it to be 0. I fix it once and for all. And then, if you believe me that the antipode does the correct job, I get here 2 times the same object. Because the first object is from 0 to S, so it's a thing running in S. It's a 1 parameter object running in S. And in the second slot, I have the same object evaluated at a different time point, but also running in 1 parameter U. So the ostensibly 2 parameter object, iterated sums signature, can be recombined from a 1 parameter object. Yeah? I mean, people who do this should remind you maybe of tensor decomposition. Yeah, something that looks like a complicated quadratic cost thing is in fact a very simple object. Yeah, because it's a product of 2 one-dimensional functions. Yeah. In general, a function f s t, f of s comma t is complicated, but there's functions, for example, g of s times h of t, which are quite easy. Yeah, and it happens that the ISS is easy in this sense. And again, we get this from Chen. So it's encoded in the Hopf algebra. And if you would have to write this down like by hand, you can do it maybe for small examples, but after that it's essentially hopeless. But the algebra takes care of this for us. Yeah. So again, the algebra takes care of a lot of bookkeeping here for us. And the question is, I want to address in the next session is now how to take advantage of this. But yeah, maybe I pause here for questions, what we have seen so far. Yeah?
I have a question. When you talk about dynamic programming, I think there is an optimization that you are solving. So you're solving an optimization.
So yeah, no optimization for me. So yeah, so yeah.
Your framework in the
Yeah. Yes.
series where the optimization.
There is no really, if you switch to an appropriate semi-ring, the min plus, for example, semi-ring, then these sums are actually an optimization problem. Otherwise, they are a summation problem. Yeah.
So you have the same structure, but
It's-
there is no optimization necessary.
No, there's nothing optimized, only in the semi-ring, or max plus, or min plus. Okay, so I want to talk about two things. The one thing is that I mentioned before that CNNs, convolutional neural network, somehow lost recently the stage to, or the first place to other methods, and this is the attention mechanism. And it turns out that iterated sum signatures have something to say there as well. This is this section, and then I briefly want to talk about two-dimensional data because I have a complexity question there, so maybe some of the experts can shed light on this. First about attention. So we want to do the following. You give me a query Q. It's a small red curve there in the top right corner. And then you give me a large time series Z, and you ask me, is Q to be found in there? Yeah. And maybe I don't care if Q is a bit shifted vertically, yeah, so maybe it's an additive constant. And more importantly, I don't care if it's stretched, yeah. So here we have an exact copy here of my query. There it hits. Here's not an exact query, it's a stretched copy, yes. So the first time point I repeat, and then I go through it, then I'm a bit lazy again, I repeat, and yeah. But I want to discover all these instances. And this is very relevant, by the way, this stretching, this is also called time warping. It's a huge topic in time series analysis because a lot of time series that you have do not come automatically with a clock. Yeah, so people run at different speed around the same lake if you record their GPS. The curve looks quite different if you draw it, but they're the same, so it's just a stretched version of the other. And this happens again and again in data science. So you really want to often mod out this stretching operation. And I should have said, I fast forwarded over it. This was the last point here. The iterated sums, they're invariant to this stuttering. Actually, the way I defined it, they're invariant to insertion of zeros. Yeah. So the expert on quasi-symmetric functions, they know that you can define them as being invariant to insertion to zeros, and this is mirrored here. If I plug in not the time series itself, but the increments of the time series, if the time series stutters, so if I repeat a value, then the increments, of course, get the zero. Yeah. So if I then calculate the iterated sum signature on increments, then this is invariant to stuttering. It doesn't care about stretching the time series. And this is very relevant. By the way, if you put in the increments, then you're really close to iterated integrals of Chen, for example. I should have mentioned this maybe for the topologists. Yeah, So Chen, of course, introduced the whole business of looking at iterated integrals back in the 50s, I think, for very different questions about loop space. Yes. And then you have, of course, the differentials of these curves appearing. And the increment is the discrete differential, as we heard yesterday also. Okay, so is the goal clear? We want to discover a time series inside another. Maybe it's stretched a bit. Maybe it's moved up or down. Yeah, it's. Then we want something like this. Yeah, we want a histogram that tells me, yeah, time series appears there and it appears there, maybe with some. You of course have noisy observations, so you can never say for sure. So what's the cost of this? If you forget about the stuttering, which makes it a bit, what's the cost of this? No, sorry, if we forget about the stuttering, this is linear cost. I just take my query and I shift it over the thing and I compare, and if it matches green light, or red light in this case, otherwise nothing. But if I want to be able to stretch, I have to compare to any intervals of this, what was it, 0 to 20 now? So this is again 20 choose 2, yeah? So it's again quadratic cost. And time series have a tendency to be long, so thousands or million time points, and then quadratic already becomes a problem. So if you do this naively, you just compare Q to any possible stretched thing there, and this works. But yeah, it turns out you can do better. You can do a lot better. This is where the ISS comes into play. Again, we want to do this in linear cost. And for this, I have one slide here on the attention mechanism. So the attention mechanism is this somehow, what if you want, kicked convolutional neural networks from its throne. In the last, what is it here now, 5 years, yeah, attention is all you need. Attention, transformer, and all its iterations, they all boil down to, if you see it for the first time, you're surprised how easy it is, but it's such a nice idea. It's very simple. It is really formulated in terms of a query and a key, so like a database, yeah. The problem is I just put 5, and 3 here because I didn't want to introduce any variables. Yeah, but I have a query in some Euclidean space. Then I have a database of keys. Yeah, and if I want to match my query against its keys, I do this with the inner product here with the dot. Yeah. So if the inner product is high, they match. If it's 0, they're orthogonal. Negative, maybe it's worse than not matching. And at each key, I have attached the value that I'm interested in. Yeah. So it's a database. Yeah. I have a bunch of keys. I can query this by forming the inner product. If this is high, I want to get the value there. So now I want to do this in a differential fashion. Yeah, it's a database. You have a query, you get one result, and it has to be the exact query. Otherwise, you do not get the result. What they do in neural networks is very simple. They create, maybe again, like in your talk yesterday, you create a probability distribution. Yeah, so the z here is the partition function, which is just it's just normalized, so you get a probability distribution. So what you do is you just match your query against every key. You exponentiate it, then you have positive numbers, and if this number is large, then you had a good match, and if it's small, then you had a very bad match. And then you normalize this to get a probability distribution, and you just take the expectation of your values over this probability distribution. So extreme case, the query matches exactly with one key and is negative minus infinity for all the others. Then the probability distribution is just a Dirac at this one key, with this one I, and then it just spits out the value. So you have a classical database system then. But here it's in a smooth fashion, so you can learn through it and so on and so on. This is more or less clear if you haven't seen attention for the first time. So it seems like a very basic, almost you're angry that you didn't come up with it, but it has been 5 years, so yeah.
What is the exponential?
The exponential is just, the exponential actually will be a problem in a second, but it's because you want to, it's a usual thing you have also like in your talk yesterday, right? You have these, you want the probability distribution, yeah? So then so you first make it positive. No, it's not, no, it's just that you need anything that maps to the positive reals. Yeah, and then you divide by the total mass and you have a probability distribution. And exponential has proven to be quite successful. Because it's also very extreme, right? If one key matches a lot better than the others, then it gets very exponentiated. So you want this. And actually this exponential is a problem still for us. I'll come to it in a second. Because the exponential is not a polynomial. This is the problem we have. So let me try to explain in this one slide how attention works in our setting. So what the idea is, instead of comparing the data itself, we compare signatures. Yeah, and I take for this example the easiest entry of the signature, just for the letter 1, just the word letter 1, and delta x here is increments of x. So instead of summing x, I sum up increments of x. So xi, del xi is xi minus xi minus 1. Okay, then Chen tells me, I could also figure this out by hand, as you could figure out everything here by hand, but the algebra does the bookkeeping for you. You can calculate this ostensibly 2-parameter object, ST, quadratic object, yeah. It's just the difference of 2 1-parameter objects. And if I spell it out here, I sum up increments, then it's just the difference, yeah. So again, this is a toy example. It's for iterated integrals people, the integral from s to t dx is xt minus xs. Okay, but this already demonstrates the core ideas. If this weren't a single letter word, then this expression would just be longer, but it would all be stuff that is just depending on 1 parameter times stuff that is depending on 1 parameter. It's really always tensors of order 1, so to speak, rank 1. Okay, and now I plug this into my attention mechanism, yeah? And again, I simplify a lot here. So I use now X is my query. Q, I also calculate the exact same thing. It's very stupid. It's just the increment, Qt minus Qs. And the values I put here, Vt minus Vs, just to demonstrate. And I even threw away the partition function, yeah? Because now I can just do algebra here. So I have here just xt minus x times qt minus qs. Multiply this out, okay? And now comes the tricky part for your question here. I say this is almost the same as identity. Exponential of z is almost z. This is of course completely wrong, yeah? It's not even asymptotically true. But let me continue here for the example, because now I can split up this sum here. Now I have a polynomial. And let's just look at the very first term here, or no, the second term here. I get a bunch of these terms. It's 8 terms now, but they all look like this. It's qt times something at t times something at s. And then summed from s to t, smaller than t. So this is an iterated sum, like we had before, yeah? So this is not quadratic in cost. This is linear in cost. Yeah, so the whole thing costs linear time. And this is the trick that works to reduce this ostensibly quadratic problem to a linear problem. So this joint work with Leonhard Schmitz, I had some simulations, but I didn't want to clutter here the talk, but maybe I should have put them. So this works up to some point. So theoretically, this works perfectly well. Yeah, the work is done by chance identity, and you can calculate and cost linear in time. There's two problems: numerical stability, because maybe I can say it here. As you might know, calculating here this times this is numerical more precise usually than expanding first and then this minus this. You get all these minus terms. You get more cancellations, less cancellations. Yeah. So this reduces numerical stability. If you expand polynomials, yeah, the results get worse. But this seems to be fine. What's the problem is that what I needed here was I needed a polynomial. I took here a linear polynomial because I wanted to separate terms, but I can definitely not take the exponential. But it works. It doesn't work as good as the exponential yet. And if we use the exponential, we have quadratic cost. So there's a trade-off here, which we haven't completely figured out yet. Okay, so this was very short on the attention mechanism. This was showing another way how we can use the Hopf algebra structure, because the Hopf algebra does all the bookkeeping for us. Yeah, we write the code, we implement the Hopf algebra. This is what we have to do. And I don't think you could have seen this without just coming from the dynamic programming perspective. The dynamic programming just tells you here that I can move one step further and accumulate. But this tells me I can really calculate any interval quite cheaply. Okay, any questions for this attention? Because then I very briefly talk about multidimensional case. I have 3 more minutes. Yeah, while you think about questions, let me thank the organizers first before I come to the last section. I saw a beautiful conference here. I highly enjoyed it. So thanks a lot. And also to the talks, this is fantastic. Really, really lots of input here. Yeah.
Thanks to Claudia and
Yeah, where's Claudia? Ah, there's, yeah, okay, yeah, there. All right, yeah, so then let me finish here with the last slide, because I have a question to you. So we don't want to do now images. Yeah, CNNs, they were invented for images, and a CNN, Tilat is, huh? Abrit?
whatever it was, let me see it. You want to open that?
Yeah.
Sorry.
So.
I was thinking it was just something that randomly happened. Internet connection might be bad.
But there it was. Okay, so that's what the CNN does, yeah? You have your little kernel, and it scans over the picture and calculates something. That's what the CNN does. And why were CNN so successful? Because if a dog is here in the picture, it's the same as a dog being here. So it's enough if I have a kernel that detects a dog and I scan over the picture, and then I can perfectly distinguish cats and dogs. That's the punchline why CNNs were successful. So how would an iterated sum look like? It would look like this, yeah? So you scan over all these 4 sets, yeah? A lot more here than these just scanning over the consecutive kernel. Okay, so this is what we want. And for reasons I try to do here with these 4 examples of a tree, we want again invariance to stretching again. Now we stretch in both directions, yeah, because the stretched dog is still a dog, yeah. So you still want to be able to, and also because of mathematical curiosity, of course, we want to do the 2D case. But there are examples where really stretching invariance is relevant for pictures, yeah. And it gets interesting. It's not just copy and paste, yeah. Because, okay, so here's the definition. I want to get to my to the one question I have. So you define certain sums. You can do it over a semi-ring. Let me just and you have maybe for the experts, you have a quasi-shuffle structure, you have a quasi-half shuffle structure, you have an NEA or quadriform structure. All this is good and nice, but chance identity, and this was the thing that was relevant to our dynamic programming. It's not so clear. We're in the process. Let me just mention that some of these sums you can calculate cheaply. So if I sum over all 3 points, all points, I should have drawn it, you can do it quite efficiently, but it appears that you cannot do this over these 4 points. And let me explain it. You could have skipped the entire talk. Let me formulate the problem now. And then hopefully one of you has seen this in another context and tell me what the exact complexity of this problem is. Okay, so let's say you have a black and white picture, yeah? And it's 15 times 15 here big. And I ask, are there 4 points in this pattern that I had before, yeah? So they are in the same line, they are in the same line, and they are in the same column. So it's like a 4 square, the corners of a 4 square. Are there 4 points that are white? So the naive algorithm costs 15 to the power 4. You can do it a bit smarter. You get 15 to the power 3. And we're sure this is a very well-known problem and has a different name, and yeah. But yeah, if somebody has seen this, I would be very interested in. But here you already see that it gets a lot more interesting. So what we hope to do is that somehow this, again, we have a Hopf algebra, it's graded and so on. We hope to slice it now according to complexity classes. Yeah, so there's a big subset which has complexity which is linear in the input data. This matrix here is one of them. It is linear in the input is quadratic. And there's stuff that is cubic, gives me another slice, and so on and so on. So that's the hope how we want to build the compatibility now with the Hopf algebra, but we're still far away from that. Yeah, okay, so let me wrap up now. So our contributions was with these iterated sums was to liberate iterated integrals from their analytic setting. This means we can work over semi-rings. This means we can put arbitrary learnable functions around them, these little f thetas. So it's a generalization that is very helpful for machine learning. Dynamic programming appears because of chance identity. Chance identity is essentially the same as the dynamic programming principle here. If you are over Hopf algebra, you have an antipode, and then you get even more. We can do fast attention. We can detect these little subsequences, and no matter how much you stretched or compressed them. And the multi-parameter setting poses new challenges. Yeah. So, yeah, happy to answer any questions. Yeah.